Suppose A and B are two sets. Show that for every relation R from A to B, R composed of the identity relation on A equals R. Alright, well that's how identities are supposed to behave, right? Whether it's a multiplicative or additive identity for the real numbers or a identity relation. Let's make sure that the left side makes sense though. So what's the deal here? R goes from A to B, and then we're doing identity on A before that. So the picture looks like this. We have A to B. We're doing the identity on A first, and then following that up by the relation R. And the equation here is saying that, well, that's the same thing as just doing R from A to B overall. Okay. So why might that be? Well, if you have an element of the composition here, then that means that you have, you have an xz such that there's a y in the middle with xy in this relation and yz in the relation R. And if xy is in the identity relation, that means that x and y have to be the same thing, right? So x equals y. And so really, this y is the same as x, and so we have x to z, okay? So in other words, the ordered pair x, z is in R as well. And then if we try and turn that around, let me make some more space here again. Okay, so if we take an element of R, namely an ordered pair x, z, which is in R, then we can always, see that that's also in this composition because we could put an x in the middle here, and then x is an identity on A, and our assumption was that xz is in R, right? And so because x to z is sort of obtained by composing xx and xz, it must be in R composed with I sub A. Okay, so that's the general idea. Let's try and write down a proof. We have R as a relation from A to B, and we're trying to prove this equality. So for that, we let xz be an arbitrary ordered pair, and we're going to show that it's in the left side if and only if it's in the right side. So I've already broken that down into two conditionals here. And let's take them one at a time. So for the first one, we can do direct proof, bring the antecedent over as a given. And then for that ordered pair to be in the composition means there exists some y in between them, right, such that xy is in I sub A and yz is in R. And we can do existential instantiation to get a y naught, for which that's true. And once we have that, well, for x, y naught to be an identity relation means that x is equal to y naught, so we can make that replacement. And if x is equal to y naught, then I could replace this y naught right here by x, right? Which I do, and then I get that xz is in R, which is my goal. Okay, so let's type that proof. We want to say that because xz is in this composition, there exists, I'll say some y naught in R, in A, in the set, such that x y naught is in the identity on A, and y naught z is in R. Okay, so where am I so far? R is an arbitrary relation from A to B. We show that, okay, so I'm mentioning this part, and then we're doing the forward direction, and then we do direct proof, so this comes over here. So we're supposing that, and we're going to show that xz is in R. Okay, so then the first thing we did here was there exists some y naught in A. Okay, so unwinding the definition of composition, we get here and then right here. So we have such a y naught satisfying those two things. Okay, and then when we get to the next line, we're going to see that x has to equal y naught. And so I will explain that by saying because x, y naught is in the identity relation on the set A. It follows that, well, for one thing, x is an A, and moreover x equals y naught. And then the last thing we said was, okay, then substituting that in this one, we end up with our goal. Okay? So substituting for y naught in the statement y naught z in R, it follows that, or we see that xz is in R, which is our goal. All right, so that takes care of that direction. Now for the other direction, let's go ahead and do the logic for it. So there it is. We start off with direct proof. And then this time we have the composition on the right side. So we write out the definition of that. There exists a y in the middle such that xy is in I sub A and yz is in R. And then for xz to, oh, well, what am I doing here? I'm looking at this as my goal, and I already have sort of something like this form, right? Yz is in R. Well, maybe I want the y to be x. And if I want this y to be x, then I want that y to be x too. So I need to get that x is an identity on A, and it definitely is by definition, right? So this is basically a tautology. I'm just adding it on to what I already know, and that gives me what I want, okay, for y equal to x. So how do we explain that? Well, we can say because, all right, well, first of all, you know, as I said, suppose xz is in R, so direct proof gets us there. That's our new goal. All right, and then from here, I can just say because xz is in R, I know that x is in A, right? And if I know that x is in A, then I know that I have that ordered pair and identity on A. So because xz is in R, we know that x is in A, right? Because R is a subset of A times B, so the first coordinate has to be in the set A. And then, okay, so therefore, if x is in A, then xx is in the identity relation on A. And finally, because we have both of these things, we have that xz is in the composition. So because xx is an identity on A, and xz is in R, it follows that xz is in R circ I sub A. Okay, and I'm getting some notices here. Good, and that was our goal, right? xz is in R composed with I sub A. So that finishes the proof.